Hello everyone, my name is Jochen Wenninger. I'm hydrologist and senior lecturer at IHE Delft in the Netherlands, and in the lecture of today I would like to talk about runoff generation mechanisms and the processes that lead to water entering the stream. In other words, the transformation of rainfall into runoff and finally stream flow. If we take now a catchment, or sometimes called watershed or river basin, as the area of land from which water flows towards a river and finally discharges out of that area by a breakthrough point, normally defined by a gauging station, we can set up a water balance for that area. The main principle behind this is the conservation of mass, conservation of water, meaning that we have certain inflows and outflows. As inflow, we can consider the rainfall falling in that area, and as outflows we have evaporation and runoff. For the short term, the runoff is defined as rainfall minus evaporation and storage change over time, meaning variations in groundwater storage and soil water storages. But for the long term we can neglect these storage changes and we can define the runoff being the rainfall minus the outgoing evaporation. The big question now is, how is that runoff generated? How is rainfall falling in that catchment being translated into the integral information of the catchment responses at the outlet point? First of all, let's define some terms to be used in the next couple of slides. What is runoff? Runoff is that part of precipitation that flows towards streams on the surface itself or within the ground. It can also be seen as the amount of water flowing through a river cross-section in a unit time attributed to a catchment. It has a unit of a length per time, often expressed in millimeter per year. If you think about an annual water balance, then it would have the same unit as rainfall and as evaporation and can be used in the water balance itself. Runoff is composed of surface runoff and of base flow. Surface runoff is the runoff that travels overland to the stream channel. Precipitation that falls on the stream channel itself is often included in that term. On the other hand, we have base flow, which is the stream flow which results from precipitation that first infiltrates into the soil and takes part in subsurface processes. Sometimes it's also called groundwater flow or dry weather flow. Stream flow or river flow is a more general term describing the flow of water in a river or stream. Stream flow often is used interchangeably with discharge. Discharge in hydrology is the volume of water flowing through a river cross-section in unit time, often expressed in cubic meter per second. If we plot now the discharge information as a continuous record versus time, we create a hydrograph. Usually that's done at a gauging station at the catchment outlet. In the upper right figure you see a long-term hydrograph for a catchment, discharge versus time, indicating high flow and low flow conditions of that catchment. In the right lower figure you see a typical hydrograph as a response to a rainfall event. We also call that event hydrograph. The shape of that hydrograph is a response to catchment conditions. First of all, the topography, like size, shape, slope conditions, are defining the behavior of that hydrograph, but also soil types, the underlying geology, the antecedent wetness conditions, and the storm characteristics are important. Storm characteristics are rainfall intensity and rainfall amount, rainfall duration, but also land use and vegetation as well as degree of urbanization are influencing the behavior of that hydrograph as a response to rainfall. So the hydrograph is a direct response of a catchment and the conditions in the catchment to a certain rainfall event. To better understand that relationship between precipitation and discharge, we can split up the hydrograph into 4 phases. Let's have a look at the first phase prior to the rainfall event. All the water which is discharging was already stored in the catchment before the event. So it's mainly coming from the aquifers, which we call base flow. Groundwater table is falling in the catchment and soil moisture deficit is increasing. If now the rainfall event comes in, the initial part of the rainfall does not directly contribute to the discharge. We have initial abstraction. The amount of rainfall is stored and intercepted on surfaces of vegetation like leaves and needles. It's stored on surface storages and depression storages, and part of it is infiltrating into the soil to decrease the soil moisture deficit. Under continuation of rainfall, we can produce something what we call effective precipitation. That effective precipitation is that part which is translated into direct runoff of the hydrograph. That is often done by overland flow, also by infiltration and percolation to take part in the subsurface flow processes, and that will lead to a rising stream flow, finally resulting into a peak value. And if the rainfall event is kind of lowering down, we have a cessation of rainfall and a decrease of discharge until the values reach ideally base flow conditions again. What are now the runoff mechanisms behind that production of runoff? Different processes that are involved in the hill slope scale can be channel precipitation. Precipitation is directly falling on wet surfaces in the catchment. That's normally a relatively small amount. Then we have overland flow processes. We have subsurface, through flow or interflow processes, water traveling in the unsaturated zone. And we have groundwater flow in the saturated part of the hill slope. So based on precipitation, rainfall which is falling in the catchment can be split up in channel precipitation, in overland flow, or it can infiltrate into the subsurface. If it infiltrates into the subsurface, it can be split up into an interflow component or a groundwater flow component. The interflow component can be a fast or a delayed one, which result together with a groundwater flow into a subsurface runoff. For the surface part, the channel precipitation and the overland flow, it forms the surface runoff, and together with the fast component of the interflow, which is often returning to the surface by return flow, is forming the quick flow or direct runoff. The direct runoff components and the base flow components from the subsurface together form the total runoff in the stream flow. To zoom in a bit more on the overland flow processes, so water that flows across the surface towards a river channel, we can split up into two different processes. First of all, Horton in 1933 defined a process which is also known as infiltration excess overland flow or Hortonian overland flow. In this case, the rainfall intensity is exceeding the infiltration capacity of the soil, and therefore water is flowing as sheet flow on the surface towards the stream. That's often the case in arid and semi-arid areas. Hewlett and Hibbert in 1967, they defined a process called saturation excess overland flow. It means precipitation is falling on saturated areas in the catchment. These saturated areas can be seen in the right figure here, defined as variable source areas. Under dry conditions, only the streams take part in the discharge process. After the start of precipitation event, near stream areas becoming wet and can take part in that saturated excess overland flow, and under continuation of rainfall, these areas become bigger and bigger. We also call that ephemeral zone of overland flow. A very important runoff mechanism in humid and temperate climates is subsurface flow, through flow, or sometimes called interflow. That is water that infiltrates into the soil surface and moves laterally through the upper soil horizons towards the stream channels, either as unsaturated flow or more usually as a shallow perched water table above the groundwater level. Often that is combined with macropore flow. Macropores are conduits, usually in the order of a couple of millimeters, produced by earthworms and bioactivity in the soil that forms a connected network in the subsurface which can transport water in a relatively fast way, faster than the matrix flow towards the stream channel. The third important runoff mechanism, next to overland flow and interflow, would be the groundwater flow component. In a normal situation, we would have an exfiltration of groundwater towards the stream, which we call base flow. That is what we've discussed before. Now during rainfall events, we can have additional groundwater flow components kicking in. One of them would be groundwater reaching and transmissivity feedback mechanisms that you see on the right upper figure. In the vicinity of the stream, we have an increase of groundwater table due to infiltration and more extent of saturated areas, which will lead to a higher exfiltration of that groundwater towards the stream due to an increased hydraulic head and gradient. And also in the upper parts of the soil, there's normally a higher lateral hydraulic conductivity, which leads to a higher transmissivity of water towards the stream. In the lower figure, you see a piston flow effect, meaning that rainwater is infiltrating and percolating towards the saturated zone far or uphill on the hill slope, leading to an increase of water table, an increase of gradient, and a push out, like a piston effect, a piston flow, a push out of old water which is stored in the vicinity of the river. What are now the dominant processes of runoff generation mechanisms and the link to topography and soils on the one hand side and climate and vegetation on the other hand? It's not very uncommon in arid and semi-arid zones that we have high rainfall rates and low infiltration capacities of the soils. That will lead to more fast surface near runoff generation processes like Houtonian overland flow, whereas subsurface storm flow are less important. In humid climates with dense vegetation, we have to differentiate between different soil types. If we have thin soils and gentle concave foot slopes, for example, direct precipitation and return flows are more important on the hydrograph formation. If you talk about steep slopes with straight hill slopes and permeable soils, the subsurface storm flow or interflow components will dominate the hydrograph, and peaks will be produced by return flow and direct precipitation effects. Also, the water balance components will be affected in different climates by these different runoff processes. If you have a look at these two pictures indicating water balance components for arid zone on the left hand side and for humid zone on the right hand side, you see the clear difference between the runoff components which are coming to a discharge value. On the one hand side, in the humid zone, we have part of the rainfall being translated into surface runoff, but the majority is coming from groundwater, because the groundwater table is not disconnected from the surface, whereas in the arid zone on the left hand side, the groundwater table is below the surface, it's disconnected from the surface processes, there's no return flow, there's no base flow, the streams are only flowing periodically or episodically, and the majority of discharge is generated by surface near components. Not only the climate influences the dominance of different runoff processes, also there's a scale issue in a temporal and spatial scale. If we focus on the spatial scale and zoom in into a local plot scale of 1 × 1 meter, we see that there are processes important about macropore, distribution of pores, connectivity of pores, matrix flow. If we go one level up, on the hill slope scale, if we talk about 100 meter, then we talk about preferential flow pathways, about extent of saturated areas. If we go one level up to the catchment scale, talk about distance of 10 kilometers, different soils play a role, different hydrological response areas. and even further in a regional scale, extent of 1,000 kilometers, the geology is taking over the dominance of defining what kind of processes are important. Finally, some take-home messages for you. As we've seen, the event hydrograph is built up by fast surface runoff and slower subsurface runoff processes. The dominant mechanisms are overland flow, including infiltration excess overland flow and saturation excess overland flow, the interflow components, including macropore flow, and the groundwater flow components. Mechanisms leading to an event hydrograph are extremely complex. In general, possible runoff mechanisms are understood, but it's impossible to generalize and apply all these processes to all natural conditions and all given situations. Scaling problems of the processes occur as well. For example, for large catchments, the drainage network, the underlying geology, and the distribution of precipitation in the basin is more important than the hill slope processes which we have discussed in the slides before.